Piotr Sierant. Okay, thank you. Okay, good morning to everyone. I'm currently a postdoc at ITFO, and I would like to no, it goes. Okay, thanks. And I would like to talk about measurement-induced phase transitions in this talk, which arise, which are a phenomena that regard behavior of entanglement in quantum circuit in presence of measurements. In my talk, I will concentrate also on the post-selection problem, which appears if we try to experimentally probe those phenomena. I will discuss a way of introducing feedback control, which conditions the unitary dynamics on outcomes of measurements in the circuit, in which in this scenario one can get absorbing state phase transitions in our dynamics. And the main point of my talk will be the interplay between the phenomenon of measurement-induced phase transition and absorbing phase transition. And the talk is based on a recent work with Sheikh Turkeshi, which was recently published in PRL. So the motivation to consider this phenomena, or one of the motivations, is that is the recent significant progress in the artificial quantum matter, including setups with ultra-cold atoms, trapped ions, superconducting qubits. In all those systems, we can get a high degree of isolation and control, which allows us to probe unitary dynamics. We can also perform measurements on those systems and probe non-equilibrium phenomena in a way that was not possible before. So the type of the systems that I will be focusing today on are quantum circuits. In such circuits, we start with certain initial product state, and we act on that product state with unitary gates that might be random. They are local, and then after a certain number of layers of such circuit, we look at the state at the output. And those systems are interesting because they can be thought of as being certain prototypes of quantum many-body dynamics. And the only ingredient of the quantum many-body dynamics that is there at this stage is just the locality of the dynamics. And one can probe the quantum entanglement growth in such systems or other features of the dynamics. Yes, so there are possibly various arrangements. The circuits I will be focusing on today are such that each of them is random on its own, so they are random both in time and in space. And now I will be interested in extending those quantum circuits in such a way that we are also performing local measurements. And then if we perform a local measurements of certain observable at a given point in a circuit, that if we just consider example of system of size 2, and we assume that we have certain entangled state, making the local measurement gives us certain result and disentangles the state, which means that it decreases the amount of entanglement that we have in our system. Then if we perform a single measurement, nothing violent changes in the system. However, if we start performing many measurements in such a way that the usually considered structure is that we have the circuit organized in layers of unitary gates and layers of measurements, and the measurements in those layers appear with certain probability p, which is the control parameter of the system, then we may have a measurement-induced phase transition in the system. And the measurement-induced phase transition in the system is a transition between volume low phase and area low phase, which differ by the scaling of the entanglement entropy of subsystem of our system. In volume low phase, it scales linearly with the volume of the subsystem. In area low phase, it is independent of the size of the subsystem. At the measurement phase transition, in those simple circuits, it scales logarithmically with system size. However, there is one important problem with measurement use phase transitions, namely the post-selection problem. The final state of the circuit depends on the measurements of the outcomes that we have done throughout the time evolution of the circuit. Each of the measurements yields, in the case of qubit, 2 results, which means that in the end, the number of possible final states is 2 to the number of measurements. And then in the setup in which we have MIPT, the number of measurements is extensive in space-time volume of the circuit, which yields to exponential overhead to exponential number of final states. And now, in order to probe MIPT, I told you that we need to calculate the entanglement entropy. The entanglement entropy is a nonlinear observable of this nonlinear quantity of the state of the system, which means that in order to measure that, we need to, in an experiment, ensure that we have the same state at the output of the system. However, we do not control the measurement outcomes. They are given to us with certain probabilities according to the Born rule. And this is the post-selection problem. If we measure nonlinear quantities, for instance, the entanglement entropy, we need to perform multiple measurements, experimental measurements on the state, and arriving at the same output state is exponentially improbable in the space-time volume of the system, which is the post-selection problem. And now, one of the possible approach which works in certain restricted class of circuits is a space-time duality approach. In here, I would like to consider other approach to the system, which is based on the feedback control. So in the setup that I have described, if we consider the state averaged over circuit realizations and measurement outcomes, it is maximally mixed. None of the measurements is preferable. We get just the unity matrix in here. The idea is to introduce feedback control, which determines the unitary gates that we are using depending on the measurement outcomes. And the idea is that such conditioning will yield some non-trivial dynamics on the left of average states. And our idea to realize feedback control is through flagged circuits. This is specific realization of this general idea. In order to do that, we extend the speed of the system in such a way that we, on each of the lattice sites, we have a classical label equal to 0 or 1, which we call flag. And then, depending on the value of the flag, we act or do not act with certain unitary gates. So now I have did some space-time rotation of this circuit. Now the times flows up, and in here we have space. At each site we have certain value of the flag, and we have our state of the system. We have unitary gates, local unitary gates, measurement outcomes, and we also consider a control operation, which might be composed out of local gates or of long-range gates. And then the unitary gates, which are these local U gates, and the control operation are used in such a way that they act non-trivially on the system if flags are equal to 0. And then if flags at given site are equal to unity, either this gate or this gate act as a unity operator. In that way, we introduce certain dynamics that to the system that will be observable on the level of the average state. Now, so let's look a bit more in the details on this setup. So let's assume that initially all flags are set to 0, so that we can act wherever we want with our unitary gates. the flags are updated to unity if our local measurements yield result state up. If that's the case, we update the flag to unity, and then let's consider an example. Let's say that those two gates, those two measurements yield result state up, state up. In that case, on those two sides, we fix the flags to be equal to unity, which means that these blue unitary gates will act as an identity operator. The same will be done by the control operation, which we choose in such a way that it will act trivially on the two sides on which we have flags equal to unity. In that way, those two sides will form an ordered domain in which the spins are polarized to be equal in the spin up state, and that this will happen in certain regions of the system. In other regions of the system, the spin this won't be the case, and then we will have an action of our unitary gates in those regions. And then, depending on the range of this control operation, we can have two cases. Either this control operation is of short range, then it will act trivially on the ordered domains. It will act non-trivially on disordered domains, and it will introduce entanglement between the sides in those domains, just as the blue unitary gates. Once it becomes long range, it can also create a certain entanglement between the distant disordered domains. Okay, and now in order to probe those two types of the dynamics that we have in the system, we consider two observables. First of all, we consider order parameter, which counts the number of the or the density of the sites at which we have spin up, and the entanglement entropy. The order parameter is linear in the state of the system. This means that we can change the order of taking this trace, meaning taking the quantum average and averaging over different circuit realizations. We can as well consider put the overbar on this state and get the same result. This means that this observable is post-selection free. We don't have to ensure that each state at the output of the system corresponds to the same measurement outcomes, and we are probing that state, and only then we are calculating certain quantity, which is the case for the entanglement entropy, which is nonlinear quantity in the state of the system. We first trace out the degrees of freedom associated with certain subsystem Y, and then we perform some nonlinear operation on that density matrix, and then we average over circuit realizations. So to sum up, this observable is simple from experimental perspective. It is post-selection free, whereas this one requires post-selection. The question is, can one say something about the transition in the entanglement entropy, the measurement induced phase transition, by looking at the order parameter? And I will argue that it is the case in some scenarios, and it might be generally not the case. So let's first examine the properties of the circuit at fixed depth. So the number of the layers of the circuit, and assume that our control operation is of short range. Then, if we look at the properties of the entanglement entropy, the blue lines, we see that there is a usual measurement induced phase transition between the volume law and area law, in which the entanglement entropy does not scale with increasing subsystem size. And then if we look at the properties of the order parameter, we see that the system starts to be ordered at certain measurement probabilities, which is the control parameter of the system. And then there is certain type of ordering transition in the system. When we introduce long-range feedback control operations, so we allow this operator A to act non-locally on those disordered domains, then the transition in the order parameter and in the entanglement entropy may coincide. Yes. Yeah, exactly. So I will dive into that in more details very soon. So for entanglement entropy, we have a transition between behavior in which it is increasing linearly with subsystem size and it is staying constant. In here we have a transition. If we look at if we consider properties at times equal to 4L, then in here it will be going to unity. In here it will be staying constant at those time scales. So, but I will very soon discuss what is the type of the criticality of this order parameter. Yet, if we fix this this time, and I will come back to this problem soon. Okay. So this is the type of the phase diagram, and I will specify this problem, which is very valid very soon. So if we have control operations with with short range, then we see a transition between volume low entanglement, area low entanglement, and only at larger measurement probabilities we see the ordering transition. This transition is the one which is easy to probe experimentally because it is measured via post-selection free observables, which are linear in the state of the system. This one requires us to post-select over the measurement outcomes, and it is hard to probe. However, as we increase the range of the interactions, at some point the two transitions may coincide. And then let us examine the dynamics of the system using still the order parameter and the entanglement entropy for various values of the control parameter. If we are below this ordering transition, and we look at the defect density, which is 1 minus our order parameter, we see that it decreases in time, and then it has certain constant value. Then there is a certain value of the control parameter. There is a power law decay of this observable, and if we increase the measurement probability then even further, we see an exponential in time decay of the defect density. This power law behavior is characteristic for the directed percolation universality class, and the power that is of this decay is consistent with this class. So in that sense, there is a transition in the system. Yeah, and then the important point is that this behavior of observable that is post-selection free is also reflected in the entanglement entropy. As you see, the behavior is the same. Of the entanglement entropy and of the defect density. Now, if we have our control operations of short range, then the behavior of the entanglement entropy is area low below the transition, and above the transition we have collapse to state with 0 entanglement entropy. However, if you consider long range control operation, we again see similar behavior of the entanglement entropy. However, now it follows volume law. If we are below the transition, at the transition it follows this decay of the directed percolation universality class, and then above the transition it decays exponentially. This means that in those cases, probing the observable that is linear in system size tells us something about the nonlinear quantities. Okay, so if I don't have much time, I will skip 2 technical slides and go directly to the conclusions. So interplay of unitary dynamics and local measurements yields measurement-induced phase transitions, which have the problem of the post-selection, because the measurement-induced phase transitions are about behavior of, for instance, entanglement entropy in the system, which requires us to post-select over the results of measurements, then measure the nonlinear observable, and only then average over circuits. If we introduce feedback control to the system, we introduce non-trivial dynamics on the level of average state of the system, which can be probed with linear observables in the state of the system, which then can be measured easily in principle in an experiment. varying the range of the control operation that we set up in such a way that it is acting trivially on regions in which we already have order in our system. We can have different interplay between measurement-induced phase transition and absorbing phase transition. In the cases that I have shown you, the critical behavior at the absorbing phase transition and the measurement-induced phase transition was the same, which means that in those cases, in this case, just looking at APT tells us something about the behavior of entanglement entropy. However, this is not generally the case. One can consider different choices of this control operation, in which even in the cases in which the two transitions occur at the same value of the control parameter, the critical dynamics of the entanglement entropy is different than of the order parameter for APT, which means that post-selection problem also with this feedback control approach is solved only in some special. Thank you for your attention. So, for instance, the superconducting qubit platforms, such as those, for instance, the ones realized recently by Google with superconducting transmos, just allow one to act with certain unitary gates that are controlled by them. So. Yeah, so then, for instance, the gates aren't taken out of certain ensemble of unitary gates, but the gates are parameterized by few random parameters that might be chosen randomly, and then gross features of those phenomena, for instance, of the measurement induced phase transition, I think stay the same. I would hope that they could do it, because in order to get from this picture to the absorbing phase transition, you just have to have certain control in which you determine the action of the unitary gates regarding using the outcome of the measurement. So if they can act with unitary gates, they can perform measurements, and they would just need to extend the system's state to include the flags, for instance, and then keep the track of the flags. And if the flags are equal to unity, they wouldn't act with the unitary gate. And this would yield the dynamics that I was. No, it's not. Definitely not. Yeah. Yeah, so it is obvious if you look at the fact that the average state is maximally mixed in those setups. So if if that's the case, then there is no linear observable, because linear, and that is independent of the value of p. At all values of p, even if p is equal to unity, which means that we are performing measurements everywhere, we are getting just a bunch of random spin up, spin down states, and then if you average, we get maximally mixed states, and then we see nothing independently of the value of p. So this feedback is necessary in order to introduce some non-trivial dynamics on the order of average state. Yeah. I listed 4 recent papers which kind of follow similar idea of using certain type of feedback operations in order to introduce some non-trivial dynamics on the level of average. Those two, the last two, consider certain types of random circuits with a similar type of feedback dynamics, in which if we have desired measure outcomes, we do more or less nothing, and then if we have the desired measurement outcome, let's say we apply some gate in order to correct it. So this is those two ideas are in some sense similar. However, for instance, one of the advantage of our approach is that this can be simulated using Clifford circuits. The flux can be easily introduced for Clifford circuits, which allow us to get to large system sizes and probe easily the regime of long-range interactions in the system. Then this work is about free fermions, and then free fermions may be quite special case, and then symmetries of the system and so on play important role in the phenomena that we are discussing. And this work considers even different setup, which I would agree is kind of similar to our case with where when A is of very long range interaction, but this is I would say a topic for discussion. Okay, so in here, okay, in those two cases, they consider just a short-range control operation, and they just conclude saying that if we have short-range control operations, we are in this case in our system or on that line, in a sense that volume law and the real law transition does not coincide with the ordering transition. And that is the conclusion of those two earlier works. And then they just say that this transition in both types of the circuits that they consider is of directed universality percolation class or something related in the second case.
I have one. The result important if you notice 1, 2, 3 based on measure.
Okay. I don't know too much about those papers. We can, yeah. So then we can discuss. Yeah. Sorry, I don't know.
Speaker, Kolovsky.
Yeah, thanks. In the last lecture, in the last week, so I discussed the many-body quantum house in open system, and these problems, in fact, is more difficult than the quantum many-body house in the conservative systems, because now the system dynamics takes place in the extended Hilbert space, where the Hamiltonian consists of the blocks, and each blocks are associated with a given number of particles in the systems, and all these blocks during the dynamics become coupled by the relaxation operator, which is usually has a Lindblad form. Okay. But in this talk, I am going to go one level down and discuss the house in open or dissipative single particle system. So then I guess the same phenomena can be also found in the many body systems or similar one. I come to the most known example of dissipative system, quantum system. This is quantum dissipative nonlinear oscillator, driven dissipative nonlinear oscillator. In the classical approach, this is the Hamiltonian of the dissipative and driven nonlinear oscillator, this is nonlinear oscillator, this is driving, and you add to the Hamiltonian equation of motion friction. Of course, it was considered very time ago. I mean, those results you can find in the first volume of the Landau and Lifshitz, and it serves as a model for hysteresis in the dissipative system. So the point is that at certain values of the parameters, you have two steady-state solutions. So one limit cycle, which is lower limit cycle with low energy, and you have also the other limit cycles with larger oscillator amplitude. And in reality, what case is realized, of course, depends only on the initial conditions. So for some initial conditions, the system is attracted to the upper limit cycle. For the other ones, it's attracted to the lower limit cycle, and the set initial conditions then compute the basis of the attractors. And these two figures shows you basis of these two attractors, two limit cycles for this model for two different values of the driving frequency. And these 2 points is essentially positions of the attractor in the rotating frame of the coordinate. This example. Okay, this was about the classical systems, and now we come to the quantum systems. I guess the first paper which addressed this question is the paper of this famous scientist from New Zealand in 1982. First, now we describe evolutions of our systems in terms of the master equation on the density metric of the systems, and in this case it has this form. This is quantum Hamiltonian, and for these problems one can solve it, at least numerically. The point is that this is still the linear equation, as all equations in the simple particle in the quantum mechanics. It can be rewritten because of its linear form in this form, where lambda with L with hat is called superoperator. And then you immediately can write down the general solutions of the problems. It is given by these equations, where lambda is the eigenstates of this superoperator. Then you again can prove quite simple theorem that among these eigenstates, only the eigenstates with zero index is equal to exactly 2, but all others have a negative real part. And because of this, during dynamics, they die out, and you are left with the stationary states, which is discussed, which is given by the eigenstates with index j equals 0. I mean, you only need to find the stationary state, you have to know only the now it is not the eigenvector, it is eigenmatrices of these equations, which corresponds to the zero eigenvectors. Well, and immediately come to some contradictions with classical mechanics, that unlike in the classical case where you have two steady-state solutions, in the quantum case we have only one steady-state solution. So it caused some discussion in the literature, but then everybody come to the conclusion that the point is that in quantum case, only one of these two limit cycles is the true steady states, as the other one is metastable states, which has a finite lifetime, and this time can be very large in the classical limit, approaching infinity. So this is, let's say, known results. And now I come to the motivation. Motivation is like this one. I want to find some other systems which is as simple as a driven nonlinear oscillator, but from which we can learn something more than we already know. And this is a double resonance model. or if it's Hamiltonian up to here, it's called double resonance because this term can be presented as the sum of two terms. And here is some simple physical realizations of the double resonance models. For example, you can consider a compass, put it magnetic coils with alternating magnetic field. It will be like this one, and this will be the arrow of the compass. Or in the quantum case, you can put the dipole molecule and put it in the alternating electric field. Essentially, you always have rotors which can rotate. Now I flash some phase portrait of this system for different value of the driving frequency. It will be my control parameters. Frequency. And this is the case when this driving frequency is pretty large. Dissipation or relaxation constants is pretty small. And this is the phase portrait when the dissipation constant is equal to 0. We have two nonlinear resonances, this and this one. The upper one corresponds when this rotor rotates clockwise. This one when it's rotated counterclockwise. And here also some secondary resonances. Now we add dissipation, and I believe this scenario is that nonlinear resonances transform to the limit cycles. So now we have 1, 2, 3, 4 resonances, and now we have 4 limit cycles. This, and this. This point is the same as this one. And different color again is the basis of these 4 attractors. Okay. Now, next, I start to decrease driving frequency, and which moves my two nonlinear resonances closer to each other. They begin to interact, and due to the interaction, you get chaotic dynamics near the center of the phase space. But again, as soon as you include dissipations, this remnant of the nonlinear resonances, these stability islands, it transforms in the limit cycles. And the only thing you now see is that the basis of the attractors all are pure fractal structure. Let's say this is the consequence of the chaotic dynamics. We go even for smaller. And now, like this one, we have now only 2 stability islands. In the dissipative case, only 2 limit cycles, and basis of the attractors now are really seems to be. Yes. Yes. Now this is completely classical. The left is without dissipation, the right with dissipation. Left shows the phase portrait, one correct cross section. The right shows the basis of the attractors. Okay, in fact, in my talk, I restrict myself to this value of nu, but if you go down, then you will see a bifurcation, set of the bifurcation, you have more attractor, and then you even have a chaotic attractor. So this is an answer for me. So now quantum dynamics. Again, we do the same. We use the spin master equation as for the quantum given dissipative oscillator, rewrite it in this form. The difference is now that the superoperator depends on T periodically, and because of this, we should construct unitary superoperator the same way as we construct the Fourier matrix, and then diagonalize it. Now the stationary states correspond to the lambda equal to 1, because this is the stationary states. All other becomes metastable. This is the spectrum, as we see, and our interest is essentially this 1, 2, 3 eigenstates close to this unity. This is the driving frequency. Sorry, that should be moved. Driving frequency. So when this is large, 2 resonances are far from each other, dynamics is regular, you have the type degenerate. vertically degenerate, but then they come closer here, so they start to split, it goes down. And they come to the unity really quite close. I mean, this is calculation for the effective H bar 0.5. If we decrease H bar 2 times, you can see that now you even see it looks like they touch the unity, but of course they do not touch the unity. There is finite gap between the upper level and the next level. And these gaps due the lifetime of the metastable states. Well, okay. Now decay of the metastable states. This is refers to the case when we have no chaos, resonances are well defined, basins of the attractors are like this, and this is diagonal elements of the first 3 matrices. So 0 with indic 1, 2, and 3. These 2 values are practically degenerate, and this is what is the diagonal elements of this one, this closed diagonal elements of this one of the third one, and here is H and action, or let's say rotation rate, angular momentum. Okay, from this 2, 3, you in fact can construct linear superpositions which initially populate only the upper limit cycle, like this one, but because these have smaller than unity, more modulus, this and this one, this die out, and then this is the steady state solutions. But you start from this one. So essentially from here, systems comes to here. In fact, here the phase structure is simpler than for the driven nonlinear oscillator, and this allows us to obtain the analytical estimate for the lifetime. At the end, we get formula which has the same functional dependence as the tunneling rate. So this is exponent where H comes in here. And here is the basis of the local attractor. Sorry, this is the local basis of the attractor. So each defined as the separatrix trajectory of this effective Hamiltonian. So you see that again, S is phase volume encircled by the separatrix, but this formula also includes the decay rate. It comes here, decay rate, and also appears here as a parameter of the effective Hamiltonian. What? Here, okay. This is the case. Let's say, oh, sorry, maybe one. So this is a double resonance model, right? It consists, I come to the very beginning, from 2 terms. This and this one. To obtain the lifetime on this one, I can simplify the problem and throw away this term. So that is the slide I'm here. How it is exactly repetitive is this case. Then you have, I thrown away this term, and so the system relax from here to the states where the others do not rotate practically. Okay, and now come with the problem. I mean, yeah, I call it house assistant tunneling, because these problems in the non-dissipative case was considered by a number of the people, and half of them participate with this program, or except experimentalists. This is experiment. And you know what it is. I mean, so if we have the system like this one, and we put the classical particle somewhere in the this stability islands, it will stay here forever. In the quantum case, however, it can tunnel from here to here, and somehow house and hence this is tunneling. This is the point. Now we have more or less the same problem. We have in this limit cycle And classically, the system will stay here forever. But in the quantum case, intermediate area appears here, and we are interested so when it happens. And how indeed enhance this tunneling drastically? It appears as soon as you come to this point where these two degenerate levels become split. When you move here, and now look only on the stationary states. So now you can see how the diagonal elements of the stationary matrix changes when I decrease omega. Here, this is large omega. We are somewhere here. The stationary states, these rotors practically do not rotate. But when we move to smaller values of the frequency, we come to this case, where the probability that the rotors rotate clockwise and counterclockwise are equal. Means that even if you begin with an ensemble of the rotors which rotates all clockwise, and you have some dissipation or coupling to the environment in the quite short sub, you have half of the rotors rotating in the opposite direction. And it's really much faster than it happens in the case of the non-dissipative system. Okay, which come to conclusions. Okay, so this is conclusion that the system double resonance models is good because it has a simpler structure than the driven dissipative nonlinear selector, which is a paradigm model for the classical quantum instability. And this allows us to obtain the estimate for the lifetime of the quantum limit cycles. For a small driving frequency, however, the system dynamics is much richer. Here with chaos means a nonlinear driven resurrectant, at least what is written is on evolutions, there is no chaos. But it appears, and this is now we address this phenomenon of the tunneling. Also, I didn't cut to very small H bar where this we have in the classical case the systems shows the chaotic attractor. And this is a point problem. You see a signatures of the transition to the chaotic dynamics. Thank you. Yes, so well, yeah, everybody understands this according to his own, but the point is indeed like this one. You mean the strong dissipation schemes of tunneling. You say so when with large dissipation, the systems behave more classically. This is what you want to say. Right. Okay, then let me try to give you some. I showed the Lindblad operator. So if you try to, if you take into account this Lindblad operator and you write the classical equation of motion, then you get dissipation, but plus irreducible quantum noise, which you cannot get rid of. So then if you wish, one of the explanations would be like this, that this quantum noise kick out the system from the basins of one attractor to the other one. And because the basins of attractor interpenetrate each other, you have equilibration. Then if you add to the classical system a little bit noise, even on the level of the Planck constant, you also will get equilibration. Okay, maybe we move to the panels discussion. Okay. And I know I didn't try to address this question. Sorry. Well, formulation of the problem is the same. But I didn't claim that the results are the same. No, I mean, I didn't study this crossover one from really to study what happening when you slowly bring resonance to each other. Well, Oh, again, I don't know exactly, I mean, the region or the parameter space where you get the strange structure, but the point is that you can get it. And this is one of the examples. So you see that his dissipation is not very strong, and the interactions between all the resonance surfaces or those. This one, in fact, this is a phase portrait. It shows it all. This is indeed the strange structure. This is indeed the strange structure. You can put this. How one is doing this? So the point is like this, and I get okay. Oh, okay. Let's even come to the further one. The opposite directions to the former one. The simpler problems without. Well, when you're dealing with stuff like this one, diesel and wrap operated stuff like this, then of course you impose some truncation parameters that the systems cannot have too many states. This is your control parameter. Then it deals with some matrix of the size, for example, 100 by 100. For initial conditions. Yes, this is what I'm trying to say. I mean, then you have matrix 100, 100, then you order it column wise and have a column vector of the size 100 squared. And then all this comes to the problems of the diagonalizing these problems with matrix 100. This L is 100 to the square. And so any initial conditions and then be mapped to some vector. One watch becomes metastable. Well, let's say when you climb here, for example, what is this way? This is upper and this is the low limit cycle. When you go to this point, the size of the attractor shrinks to zero of this one. And if the size of the basins of the attractor shrink to zero, then any tiny noise can kick out the system in the basins of the blue. And that counts to the blue. Through energy. No. No, I have no figures, but I do
Sorry. I'm not quite sure if you can hear me, but the speaker's audio is muted, so I can't hear anything.
Can you hear me now?
Perfect. Thank you very much.
Okay, so here you good with my screen. Let's see. If that's the play button is hidden. Ah, okay. Thank you. Okay, so the last thing I was saying was in this with the Fisher information is the error kind of optimized over all measurement operators, but actually the optimal one can be very, very complicated for a many body system. So both approaches have their own value. This is something that you can calculate, for example, for observables that are easily accessible somehow in whatever setting you're looking at. Whereas the Fisher information is useful for these fundamental bounds, but the actual observable to achieve that might be very complicated. So a common scenario to kind of by the discussion a bit is to look at pure states only and unitary dynamics. And not only that, but the unitary dynamics is generated by a Hamiltonian that looks something like this. So the parameter you're trying to measure is just a factor in front. And then the Hamiltonian is a sum of local operators for each of n different particles in your probe. And if you go through the calculations of the error of the quantities that I mentioned in the previous slide, then you can work out what the error looks like in these cases. And if you choose an initial state that has no entanglement at all, then the best you can do is what people call the standard quantum limit. So you have this scaling of the error, of the bound for the error. It's 1 over the square root of t n t. Or if you allow entanglement for your initial state, then you can do better. So there's an enhancement that's possible by exploiting entanglement in the initial state. And in that case, you can have an enhancement of the square root of n, the square root of the number of particles in your number of probe particles you have. But in either case, what you want to do is you want to optimize the denominator. You want to maximize the denominator here. So you want to increase n as much as possible. You want to have many probe particles in your system. You want to increase capital T. So that's essentially having as many repeats of your experiment as possible. And you want to have a large little t. So you want the evolution time, the sensing time to be as large as possible. And each of these, if you can make them larger, gives you better precision in the end in estimating your unknown parameter. So you can see that if you try to increase n, for example, you're getting a much bigger system, maybe a more complicated system. If you're increasing t, little t, then this sensing time is increasing. And in both cases, this kind of approximation of your Hamiltonian, where it's a non-interacting Hamiltonian, just a sum of local observables, this might start to break down. You know, if you have very long interactions and other Hamiltonian terms, for example, interactions between your particles might become relevant. And this is usually a bad thing for quantum metrology. So usually the interactions between your particles, for example, will lead to thermalization, which will diminish the sensitivity that you can estimate your unknown parameter with. So here, this is a typical type of scaling you have when you have these additional interactions between your particles. Instead of having a t in denominator, you have a t star, which is somehow optimized. Because in this case, you have a competition between the accumulation of signal, so the accumulation of the dependence on the parameter omega, but also the competing effect of the thermalization. So these are kind of battle against each other. And in the end, there's going to be an optimal time where you have the balance between these competing effects. And so this T star is limited in this case, which reduces your overall sensitivity. And if we understand thermalization through the eigenstate thermalization hypothesis, so if the system comes to some thermal equilibrium because the eigenstate thermalization hypothesis is true, then this gives us a framework for working out maybe how we can get around this problem. So the standard approach, would be to suppress all of the unwanted interactions in your system as much as possible. So to have this H int, this extra term, much as possible to extend your T star, which is kind of you can think of as dephasing time or thermalization time, to extend that as much as possible. But the alternative approach that I want to think about is how we can exploit other violations of ETH to enhance the estimation in these kinds of problems. So for example, MBL or quantum many-body scars or Hilbert space fragmentation, these different violations of the ETH that Valentina Ross mentioned in her lectures last week. So there was a recent paper actually on the archive about exploiting Hilbert space fragmentation for quantum metrology, but I want to talk about many-body scars. So this is a slide that's been shown, I think, a good few times through the last couple of weeks about many-body scars. So I'm going to say that they're rare non-thermal eigenstates, so eigenstates that violate the ETH in a background of thermal eigenstates. They're often characterized by having low entanglement entropy. So that's shown in this plot for the PXP model. There's a band of low entanglement entropy states, and then the bulk of the states have this higher volume law scaling of the entanglement entropy. And they're often also characterized by having this roughly equal spacing and energy omega. And if you can find simple initial states in the scar subspace, then starting from these simple initial states that are superpositions of the scars, these roughly equally spaced energies, then you're going to have long-lived coherent oscillations. And so again, for the PXP model, there's a simple initial state, the Neal state, the Z2 state that has a large overlap with the scars. And this plot has been shown a few times actually already in the last couple of weeks. This is the experimental data showing the long-lived oscillations in the Rydberg atom experiments, for which the PXP is an effective Hamiltonian. And so the oscillation happens at this related to this frequency omega, which is the gap between the scars. And so there's information about this frequency omega, which is our Hamiltonian parameter. This information is encoded in the oscillations, which are long-lived. So can these long-lived oscillations due to quantum many-body scars be expected for quantum metrology that's robust to the interactions that are in models like these models with scars? Okay, so I'm going to give you an example. So this is going to rehash everything I've said in the last few slides, but in a specific example. So the example is n spin-1 particles in an unknown magnetic field omega that you want to estimate. So this is the Hamiltonian, the Z magnetic field for n spin-1 particles. And this is kind of the ideal case, let's say. So you start off in this kind of tensor product, the product state of up and down for each spin-1 particle. And then as it evolves by this Hamiltonian, you just get this phase difference accumulate to the spin. So this is essentially, if you want to think of the block sphere made up of just the plus and 1 states, then this is just precession around the block sphere. And the observable I want to measure is this O, which is something like an X or a Y Pauli operator in this block sphere picture consisting of the plus and 1 state. And so this observable just oscillates. And if you do the calculation for the error, the delta omega for estimation of this parameter, then it has this form, which is just the standard quantum limit, which I showed you before. Standard quantum limit because there's no entanglement in the initial state here. But if we add in interactions, so here I've added in this interaction term with this, it's kind of a flipping of alternate of spins in the n position and the n prime position with some phase phi. And if I set this phase phi to 0, this interaction, you can see, has the effect of destroying the oscillations and really damaging the error here. So there's not this monotonic decrease in the error with sensing time, but actually we hit the optimal value. So I call that delta omega star. And this optimal value is, if you wait too long, then the thermalization takes over, and anytime later, and you tend to lose information about your unknown parameter. This case, the error goes like this with T star, so the optimal time where you should do your measurements, scaling as 1 over lambda, where lambda is somehow just the overall strength of this interaction term. And this isn't very surprising, actually, because this is a non-integrable Hamiltonian. If you do the level statistics, you find very good agreement with the GOE. And this is true, actually, all values of theta in this interaction Hamiltonian. So we can plot this or the ratio between the adjacent gaps, level spacings, and it follows the GOE prediction for. So the fact that the metrological performance is not very good is not really surprising. But actually, if you increase this phi parameter to pi over 2, let's skip the slide. You increase this phi parameter towards pi over 2. What you actually see is that this T star, the optimal time, becomes extended. And the oscillations of the measurement observable actually tend to recover and come back towards the perfect Rabi oscillation. And you can numerically fit this T star and this measurement and find what it looks like, and you get an expression like this. So the T star, the optimal sensing time, has this type of behavior and this dependence on phi. So you can see that it diverges at phi is equal to pi over 2. And this is saying that we're recovering the ideal case as if there was no interactions at all. So this case, this is being recovered when phi is equal to pi over 2. Yes. Okay, so this is actually arbitrary. You can choose anything you want. These can be nearest neighbor, or it can be decaying quickly with distance. Yes. Is that okay? Yes. Yep, it can be random as well, and it still preserves the scars. Well, I haven't told you yet that this is scarred, but I guess it's not a big surprise. And so they can be random. Okay, so in the numerics here, this lambda I have as I think I have lambda n prime is equal to lambda over n minus n prime squared. So something that decays polynomially with distance and an overall strength lambda. So yeah, the reason this is happening is because at these special points where phi is equal to pi over 2, then this Hamiltonian has many-body scars. So there's these states, psi s, which are perfect eigenstates of the Hamiltonian. And these psi s, we know exactly what they look like. They can be constructed in this way. So if you start the fully polarized state with all spin ones pointing down, and then you build a set of scar states by applying this raising operator, J plus. This is how J plus is defined. Then you can build a set of n+1 scar states. And actually, the initial state that we started with in this protocol is just a superposition of these scar states. So it's completely contained in the scar subspace. And as you evolve in time, you remain completely inside the scar subspace. So this can be thought of in exactly the same dynamics as there was for the interacting system where there was no interaction at all. Yeah, hope to. Okay. Oh, this is a picture just to show. Well, I've added an extra term. It doesn't affect the results very much at all, having this extra. This is just a sum of local terms, but it actually gives a nicer picture in terms of the scars. So this is a certain observable. It's counting the projector onto the 0 state of each spin 1, the sum of the projectors. And you can see a very clear separation between the bulk of the eigenstates of the model and the scar states down here. This is the entanglement entropy. And again, you can see a very clear separation between the volume law states and the scarce states down here. Yes. Yeah, so yeah, so this is the okay. So I can only give some of the details, but there's more in this paper, and including another example with the PXP model, and also in more recent work with Sylvia and with John Gould's. This has been extended in this paper, and this paper was inspired by, partly inspired by this PRL by some people in this audience, Sylvia, Jean-Yves, Zako, and others from Dublin. And so the idea of this paper, well, okay, what this paper was that another way to identify scars is through the multipartite entanglement structure. So I showed you before that scars have low bipartite entanglement entropy, but actually they have very high multipartite entanglements compared to the rest of the thermal ligand states. So that's what this shows. The measure here on the horizontal axis is the quantum Fisher information density, which Rosario Fazio's lecture last week showed as a witness for multipartite entanglement. And so what we did in this paper was we found a way to add an additional term to the Hamiltonian that breaks this even spacing between the scarce states. So the blue is where this addition to 0, and you see the blue has the even spacing between the scarce states. But if we add this additional kind of nonlinear term in the scarce subspace, then we can break this even spacing, and this can be used to generate multipartite entanglement in the scarce space, starting from a product state. And this can be used then for entanglement enhanced metrology. But the details, I don't have time to go into details, but the details will be in this paper. So just to mention some of the challenges and maybe some further questions in this topic. So I think I've shown you that the many body scars are robust to some very strong interactions, but it requires to have the perfect robustness, you need to be exactly at this phi is equal to pi over 2 point, or the phi is equal to minus pi over 2 point. And this plot shows how the sensitivity, the estimation error, delta omega, changes as you vary away from this perfect point. And you can see that as you move away, it's kind of a very sharp dip to low error at pi over 2. But as you vary away a little bit, then it gets worse quickly. So this is something that we hope to improve. And one possibility is that in the PXP model, it's been shown that the revivals from the scars can be enhanced with periodic driving. And this hasn't been considered from the point of view of metrology in these scarred systems. So can this periodic driving somehow stabilize the scars in a way that can make us less sensitive to small variations in this parameter phi? And another possibility is that decoupling is something that's used commonly in quantum metrology. The idea is if you have unwanted terms in your Hamiltonian, you can apply pulse sequences to cancel off the unwanted terms. Here we have a Hamiltonian where we don't have, this is not necessarily an unwanted term if we're at this perfect scar point. So there might be a bit more flexibility in designing dynamical decoupling sequences where there's some terms that you're still allowed to have in your system and still have quantum metrology. Okay, that's the end of my talk. So they, as the case of entanglement enhanced metrology, so they assume that you can prepare a GHZ state in whatever system you've got, and they look at the sensitivity in that case. And they actually, one of their main claims is that it's more robust to this kind of fine tuning that's needed in this scar case. But yeah, beyond that, I don't know the details too much. I don't think so. And actually, so in the problem that I'm looking at, it's important to have these coherent oscillations. So for example here, you know, the dashed line is coherent oscillations. So the scars are thermalite. Whereas in this, I'm not sure you can avoid the dephasing. Other metrology problems can adapt to the setting in NBL. Yeah. No, but I don't think that's the setting I'm looking at. You know, at least in the first part, then everything is, there's no entanglement involved at any stage. So I start in a completely separable state, and in the ideal case, I'm still in a separable state at all future times. So in this particular example, entanglement isn't needed. Yeah, I think there is, might know more about this topic than I do, but I think there is quite a lot of work about exploiting critical points for quantum metrology, because based around the fact that the Fisher information, which I showed at the beginning, so quantum Fisher information can become very large around critical points. So yeah.
No, 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 no.